I'm delighted to welcome as our next speaker, Dr. Jo Wolff from the University of Edinburgh, who's going to tell us about realism and conventionalism in measurement theory.
Okay. Well, thank you very much for the introduction and for having me here. I'm a philosopher, so I've been asked to talk about the philosophy of measurement, which is a huge subject. So I've decided to talk about a particular area of this. And I'm going to start my talk with the same quote as Hassuk did. However, it's more of the quote. I also got a picture of him, so slightly different version of this. But crucially, I think one reason why measurement has become sort of a central interest in philosophy of science is overall the development since Thomson, the increasing use of measurement across the sciences, but also beyond the sciences. And so that's been something that philosophers have picked up on, have started to worry about, and have, I think, said some good and some not so good things about. So what I'll be focusing on, though, is a particular aspect of measurement, which is quite different from what we've heard today for the earlier parts of the session here. What I'll be focusing on is this idea that what we do when we measure is we express something in numbers. And I'm going to be very interested in this idea of expressing things in numbers. What does that take? And what do those numbers mean? So that's what I want to focus on. And that's obviously not all that philosophers of measurement do. But that's one thing that I think sometimes is lost as we sort of focus on the lovely, fascinating instruments that we use to measure, or indeed the heroic romance of how we do the actual measurements. So the brief outline of the talk is as follows. I'm going to talk about what measurement is as numerical representation. Then I'm going to outline what I take to be three broad strategies that people in what is called measurement theory have taken. Then I'm going to talk a bit about the most comprehensive theory of measurement we have, the representational theory of measurement. And then finally, I'm going to make good on this claim that I talk about realism and conventionalism. I'll say a bit about where we are with respect to that today. Okay. Now, when I say theory of measurement, I should start by saying there's two broad theoretical approaches to measurement, if you like. One is metrology, which obviously we learned a lot about already. And you might think that's broadly concerned with things like standards, obviously, definitions of crucial terms like precision and accuracy, instrumentation, generally speaking, right? How do you implement certain measurements? And that's been of interest to philosophers, and that's influenced greatly, I think, the philosophy of experimentation, history and philosophy of science, also the sociology of science. So that's an area where there's a lot of work done in those fields of philosophy. On the other hand, measurement theory is slightly different. Measurement theory starts from and works primarily with the mathematical foundations of measurement. And as I've said, measurement qua numerical representation. What does it mean to use numbers to represent things? Why is it that when we express things in numbers, we get the sort of rich, interesting knowledge that Lord Kelvin was after? And why is it that we don't seem to get that knowledge when we aren't able to express things in numbers? And if that is so, what does it take to express something in numbers? Can I just throw some numbers on something I want to talk about, and thereby it looks and sounds scientific? Or does something more have to happen, and if so, what is that? And so philosophers have been quite interested in that as well. One area that people have talked about, this is obviously in the philosophy of mathematics. They worry about how you apply something as abstract as numbers to something as concrete as physics. They also worry in general about philosophy of representation. What does it take for something to be a representation of something else? And if something is a representation, does it have to resemble the thing it represents? And if not, why can we sometimes use representations to draw inferences about the thing that's represented? So there are worries here that philosophers have picked up that apply to the specific case of numerical representation, as we shall see. The last one I'll mention here, which is the field that I officially work in, which is metaphysics of science, which might sound really bizarre, but is really an honest attempt by philosophers to say, well, we know that science is discovering a lot about the world, so when we sit down and try to think in these very abstract, very deep, you might say, ways about what the world might be like, maybe we should pay some attention to what science has found out. And so metaphysics of science tries to do that, tries to look at what science has found out and tries to figure out how that fits into the sorts of things metaphysicians want to say. All right, so that's a sort of a broad map. As I said, the part of this we're going to be on for this talk is the measurement qua numerical representation side. So why do we need an overall theory of measurement, right? So why aren't we just getting on with measurements as we move through things? Well, one big reason is, again, this Kelvin idea. You have to have measurement if you want to be a science, right? So if you're not using numbers, if you're not expressing things in numbers, then somehow what you're doing is of a sort of meager and unsatisfactory kind. So that's one reason. Another reason is the idea that you have different sciences coming together to answer questions together. Big science. You're producing a measurement, you put numbers on things, but then in order to answer the question, to tackle the problem that you're interested in, you also have to use other people's numbers. Well, you have to know what those numbers mean. You have to know where they came from in order for that thing that is then presented as the answer to the problem to really have meaning, to really be a meaningful result. In order to do that, you need a lot of infrastructure. We've heard some of this infrastructure earlier in Richard's talk. Obviously, you need metrological standards. You also, I suggest in this talk, need to have a shared understanding of what numerical representations mean. Related to that is this third point. One of the things that sociologists of measurement have focused on is this idea that numbers are portable. Numbers seem transparent. Numbers seem like the sort of thing that if they're introduced once, everybody else can pick them up and use them again. Unlike concepts, which are often contested, which are often used with slightly different meanings. Well, that's true, but numbers are only as portable as sort of the epistemic infrastructure that sustains them. If you don't have that, the numbers are not actually very portable. I'll give you sort of a quick example of the sort of problem you might run into. So those are weight plates over here. You can find them at a gym, and you can find numbers on them. These are numbers with a unit, so 10 kilograms above, 20 kilograms below. If I go to a gym, even if I've never been there before, I can rely on the fact that the black plate will be twice as heavy as the green one, right? That's something that those numbers will tell me, and I can make a legitimate inference to that. That's good to know for me if I'm loading my barbell. I can't make the same inference in the case of temperature. So just because I look at my thermometer and I say, oh, it's 20 degrees, great. If it were 40 degrees, it would be twice as hot. I'd be making a mistake. And I'd be making a mistake because we know that temperature, at least as it's measured on these kinds of ordinary thermometers, is what is called a log interval scale. It's an interval scale, so I can compare the intervals, but I can't compare ratios. I can only do that on ratio scales. Crucially, if I had the whole thing in Fahrenheit, as I do on this side of the thermometer, we can see if I go up from 20 to 40 here, I do not end up with a double number on the Fahrenheit side, right? That would be 120 if I doubled it, but 40 is actually below 120 here. So that tells me, that alerts me to the fact that I can't say meaningfully that a 40-degree day is twice as hot as a 20-degree day. That's nothing to do with sort of this thermometer or with me being bad at math or anything. No, the problem really is temperature is not measured on a ratio scale, whereas mass, or in the local Earth content weight, is measured on a ratio scale. So that allows me to draw an inference here, but it prevents me from drawing it there. Now, one of the consequences of this is that maybe you cannot literally be twice as smart, even if you've read that book. So maybe that's just not the sort of thing that you can double. But that gives you a sense that it might actually be really important to understand which sorts of numbers you can know what sorts of things with. And this is what measurement theory is primarily about. So what measurement theory wants to know is, what do the numbers that we've assigned mean? One thing that you might need to know is, how do we assign them? you might also want to know, when are two numerical representations equivalent? When is it okay to switch units? Why is it okay to put both pounds or kilograms on the weight plates, and it doesn't make a difference? I just have to adjust the numbers. Why is that okay? You might worry, what is objective and what is merely conventional in my measurement? Right? The units presumably are purely conventional. Is it also purely conventional that I measure some things on ratio scales? Or is that something that's something to do with the thing I'm measuring? I would like to know. And finally, and crucially, and this will influence, of course, this will be influenced by the earlier answers, what sorts of inference can I draw from the numbers? And again, recall, one of the reasons we're interested in this is that we're not only dealing with the numbers that you yourself have generated, but also with the numbers that you're getting from others that you're trying to integrate into your theory. So those are the questions that measurement theorists worry about. And I've formulated this as a question of realism, because one very broad way of asking this question is to say, what in our numerical representations is real, objective, out there, and what is merely conventional? So that's what we want to know. So here is a way in which measurement theories have sort of tried to think about the different elements that go into this. So one thing you might have is you might have a procedure here. We'll keep it very simple, no complicated procedures here. You have a balance, and you notice that sometimes the pounds will be even, they'll be balanced, and you can think about what that says about the two weights that you put on, or the three weights that you put on these pans. These don't initially come with numbers. At some point, somebody put numbers on those. Right? So you might just have started from ones that don't have numbers. You also know that you have numbers. Right? So we have a sense of how those work. And what we want to get to is we want to know why we can have those kinds of representations, why those are okay. Why are those, assuming for the moment that they are, and I'm very confident they are, why are those meaningful representations? Why is this a good way of expressing what's going on here? Why is this, in fact, good, solid knowledge, and not knowledge that is perhaps misleading, like it might be in the twice as smart case? And I'm distinguishing three different approaches to measurement theory, which I think each take a different starting point from the slide I just showed you. So on the one hand, they're the axiomatizers. Those are people, and again, these are incomplete lists, so if somebody's missing from the list, let me know and fill them in. And these are early days too, so obviously this is sort of going back a while. But the axiomatizers, many of them come out of what I might call the German axiomatic tradition, German mathematical tradition. They start from numbers and figure out what quantities might be from that. Then they're the operationalists. They start from looking at particular measurement operations and try to think about, well, how can we put those into numbers? And finally, you have people who worry about what they call the problem of coordination. They start from experience and wonder, how could something like experience, which is so thoroughly qualitative and subjective, ever become something that is numerical and ostensibly objective? So those are slightly different ways of worrying about it, slightly different approaches. I'll say a bit more about each of these in turn. So the axiomatizers, if you like, they start from numbers, and they say, well, we know some things about numbers. We know they can be ordered, we know they can be added, we know they can be multiplied. And in order to capture these features of numbers, we have axiom systems of numbers. In fact, some of the people who I just showed you as axiomatizers were very much involved in axiomatizing arithmetic, so they were very familiar with this idea of thinking about numbers in terms of the axioms that they obey. Examples of such axioms might be association and commutativity, so axioms that you still find in textbooks of arithmetic. And from those, so these things are the starting points. From those, they deduce what sorts of features measurable attributes, that is, attributes that can be represented numerically, must have in order to be correctly numerically representable, in order to count as quantitative. So that's one strategy. The resulting view is the idea that you get numerical representations because some physical attributes are quantities. And they're primarily really thinking about physical attributes, like that's their sort of main set of examples. And the resulting view is one that I've called restrictive realism. Restrictive because only some attributes qualify. Not everything is going to be a quantity. Realism because I think they ultimately think there's something that these attributes have. There's a feature that is being captured by the numerical representation. Okay, that's school number one. The second set of guys start from a measurement operation, not by accident. So Bridgman, obviously a physicist, working on pressure measurements. Stevens, a psychologist, psychophysicist, trying to figure out how to get measurements of certain attributes and how to represent those numerically. Right? That's what they're working on. And Stevens comes up with this idea that really, for any such thing, you start from your procedure, you assign your numbers according to some rule, but you have to say how you're going to assign them. But then what you're going to do is you're going to qualitatively axiomatize that operation, that rule, and from that he derived numerical representations of different strengths. And that's really the important part here. So how might you imagine this? Well, you start from perhaps a particular physical or psychophysical procedure. You then ask, well, can I order what I'm getting here? Can I order the objects, or can I order the answers that I'm getting? Can I concatenate them? Well, it's going to be harder as soon as you get into psychology. It's not really clear what sort of things count as concatenations. And based on that, based on what the answers to those questions are, you then say, well, I can get numerical representations, but they will have different strengths. There will be, the numbers will capture sort of different levels of measurement, as it's sometimes said. And crucially, he distinguished between nominal, ordinal, interval, and ratio scales, where sort of most of the sort of classical physical quantities would be the sorts of things that you get on ratio scales, so mass and length. Those will all be ratio scales, whereas some of the things that you might get in psychology or in psychophysics might only be of ordinal or interval level. Interval, remember, that was what temperature was. Right? So you can compare some things of it, but not necessarily form ratios of it or add them to each other. So that's a different strategy. You get a different view. The resulting view is not one according to which there's a special class of attributes, quantities, and those you can represent numerically. Instead, what you're getting is, well, we're going to devise all kinds of measurement procedures. We would like to represent that numerically. We just have to be very clear about at what level we're measuring. Is what we get out of this a purely ordinal measure where I'm just basically ordering things? Or is what I'm getting something that's really a ratio measure where it makes sense to compare and add things to each other? So I call this eupermissivism because it doesn't think that what restricts numerical representation is something out there. Instead, what restricts it is how clever you can be in coming up with a measurement procedure. That's the only restriction on it. I should also give a quick shout out to Uliana Feist's recent book on operationalism, which I think explains a lot of what the sort of background motivation of people like Stevens was. Okay, final strategy, which I call coordination, which may be less of a strategy and more sort of setting a problem. And it's a problem that doesn't just pertain to measurement. It's a problem that goes far beyond measurement per se, and it's a problem that I think arises particularly if you're a very solid empiricist. If what you firmly hold on to that is what makes science scientific is that it's empirical, and you take a fairly restrictive notion of what counts as experiences. So the basic problem is this. Here are experiences. Those are meant to be the evidence for the sorts of scientific claims you want to make. Over here is our theory, and that can be quite far away from our experience. Right? What we say in our theories can be quite distant from what's going on in experience. And so we have a problem, both semantic and epistemic, of connecting what's going on in our experience with what we want to say in our theory. So I need to somehow link both in terms of the meaning of the term and in terms of what counts as evidence for what, the sorts of things I can actually observe, as Hasso just reminded us, which are often very limited, to the sorts of things I want to say in our theory. So here's an example that has nothing to do with quantitative representation, which is a cloud chamber. And you might say, look, here's one type of track which is straight, and there's other types of tracks which are curved. And I associate this, I coordinate this observation with a theoretical statement like there are alpha particles and electrons in this cloud chamber. And in fact, neatly on this particular image, somebody has done that for me. So you can see, you point to some part of your experience and see this is what an electron is. Some versions of this view say, and that's the meaning of these terms. I'm a bit skeptical of that view, but at the very least, it seems plausible to say this is some of the evidence we have for the existence of these things. Now, the same problem arises with respect to numerical representation. Because here, too, remember, we have this observation. Oh, look, if we put these weights on these pans in this sort of way, then these pans balance. Great. But then I actually need to do something to coordinate that with the theoretical statement, the weight on the left is equal to the weight on the right. Now, that's an actual interpretation of what I'm seeing here. It's perhaps one that seems a lot closer than the cloud chamber one. I don't know. People might differ in terms of the response to this. But what the empiricists were very, very keen to emphasize here is that this act of coordination needs to happen. Without it, you can't actually say that this is a procedure for measuring weight. Now, the resulting view here is often a form of conventionalism about numerical representation, because it turns out that there's a really vast gap between what we observe and what we numerically represent. And how do you fill that gap? Well, you fill it by what they call coordinative definitions, by just saying, look, we shall in future treat pans that are equal as the weight on the left is equal to the weight on the right. Let's just stipulate that this is how we're going to read pan balances like this. Okay, now, how does this relate to questions of realism? We've seen three different strategies. And I want to say in those three cases, they're using slightly different versions or different definitions of what counts as real. So the axiomatists, the green ones up there, they, I think, work with the notion of the real as what must be presupposed to make sense of a current practice. So what do we need to assume about the attributes we're representing for the numerical representation to make sense? And that's what they're trying to figure out. And that's what they're arriving at by looking at what sorts of axioms hold true of numbers. The operationalists, the blue ones in the middle, they, it turns out, through Stevens' idea of levels of measurement, end up with a version that says what's real is what's invariant across representations. I'll say a lot more about this when I talk about the representational theory of measurement, so I'll be brief on this now. Finally, the people who worry about correspondence tend to say the real is what's out there. Right? The real in my representation is what corresponds most to what's out there. So three different notions of realism. They could coincide. Okay, they're not contradictions. But those are different animating ideas about what's real that are behind those three approaches. Now, the representational theory of measurement is, I think, an attempt to combine these approaches in some ways. And it's mathematically incredibly rigorous. It's philosophically a lot less clear. The most famous publication of this are these three volumes published over the course of 20 years, authored by 4 different people, one of whom, Suppies, was a philosopher. The other ones were psychologists primarily, or in the case of Tversky, I think an economist perhaps. And they develop a sequence of mathematics, prove lots and lots of theorems, basically. These are mathematical textbooks. But they begin with this very provocative statement about measurement, which I think a lot of people have read as definition and gotten very upset about, because they say, Measurement is the construction of homomorphisms, scales, from empirical relational structures of interest into numerical relational structures that are useful. It's not the most user or reader-friendly way of putting it. What they have in mind is something like this, I think. Here is a sort of poor image of what you might call an empirical relational structure, which might well just be some objects that you've put together in some way, the kinds of relations between them. And what you do when you measure is you then have a function that connects those to the reals or some subset of the reals under some operation, like addition. That's what they have in mind. They think that's the fundamental feature of measurement. Now, I think having heard all this morning's talk, you know that that's not going to be a good definition of measurement, because there's all this stuff about instrumentation and doing experiments and setting standards that's somehow absent from this. So I'm just going to say what they really have in mind is numerical representation. Okay, this is what numerical representation is you map some structural features over here into some structural features in the numbers. That's what you do. And I think that's a fair way of characterizing what they're actually doing in those books. Okay, now, as I said, they try to combine these approaches I've mentioned before, and I think what they're combining is axiomatizing and operationalizing. So how do they do that? Well, they, on the operationalist reading of RTM, they start out by talking about how you might axiomatically describe what they call an empirical relational structure. So this is reminiscent of Stephen's idea that what you do is you give a qualitative axiomatization of some measurement procedure. Then you prove something, which they call a representation theorem. That is, you prove that this sort of function here, that function that connects this structure that you've characterized to the numbers, the real numbers. So that's what you do next. And then you prove, crucially, what they call a uniqueness theorem. That's really important because it tells you how unique the representation is that you've gotten out. That is, how much you can transform that representation, that numerical representation, what sorts of weird things you can do with it, and still have an equally good, legitimate, equivalent representation. That matters for the sort of easy, well-understood case of swapping out units from kilograms to pounds. We can do that. We know those are, at least mathematically, equally good. Of course, they might, for other reasons, not be equally good, but at least mathematically, there's no problem here. And what they show is how this works for all these other kinds of scales that aren't ratio scales. So that's useful. You could do an axiomatic reading of this too, which I think also has a basis in the development of these theories, where rather than thinking that what you axiomatize qualitatively at the start is some sort of known measurement procedure, you instead just start from some axioms that you think might be of interest. And then you say, well, let's see what sorts of representations I can get from those. And that's what's been done, I think, since the 80s quite a bit. And it's sometimes called abstract measurement theory because somehow what we've just done was not abstract enough. And sometimes you can get results there that are basically pure mathematics. They have no connection to any known measurement procedures. Now, the reason I mention these two approaches is that I think it shows you that while they do merge these two ideas, axiomatizing and operationalizing, they are at a slight tension when you read those books. And so that's generated quite a bit of discussion in the philosophy of measurement and in nearby areas. Now, what is the crucial thing? What do they do different? What's the new thing that they've done? I think crucially, they have extracted from these two, the axiomatic and the operational tradition, the idea that what matters for numerical representation is structural similarity. So it's not really about numbers at all. Numbers are quite accidental features, so to speak. What matters is that you have an algebraic structure that has a certain axiomatization. So it doesn't really matter if those are the real numbers. It doesn't really matter if the operation is addition. It doesn't really matter even that the numbers at all. Right? So the second volume of this is all about geometric representation. So structural similarity is the crucial feature. That's what's preserved, that's what's being represented. And that's what's enabled them to unify this idea that comes from the operational tradition, that you have levels of measurement, with the axiomatic tradition, which had this very restrictive realism that said we need to start from the features that numbers have to understand how numerical representations work. So in pictures, you have the axioms, and the crucial thing is they describe both what they call the qualitative or the empirical structure and the numerical structure. And because they share these axioms, you can then prove these representation theorems between them. So that's nice, formally. A lot of people say it's not extremely useful at all for people who do measurement, and that may be true. Okay, the other key thing for philosophers, again, mainly perhaps for philosophers, is that they really lean into this idea that something is meaningful if it is invariant between representations. Because one thing that they come across very quickly and very obviously is for any one such function that you prove, for any representation theorem you've proved, there's always other functions, other maps that will do just as well. And if that's the case, then you can have very different numerical representations. Again, if that's way too abstract, think of kilograms and pounds, perfectly fine, both work. And if that's the case, then there's something that you need to sort of step away from. You can't insist that the black weight plate can only be labeled 20. You have to realize it could also be labeled a different number in a different unit. That would be fine. And as a result, you have to assume that at least some aspect of your representation is conventional. What RTM insists on is that the only thing that's meaningful in your representation is what's invariant across all the representations that you count as equivalent. Anything that's not invariant, anything that changes from one representation to the other, that's strictly speaking not meaningful. And that includes such things as certain relations, right? So if my comparison of temperatures isn't stable across different representations, like Celsius and Fahrenheit, if I double my temperature in Celsius and end up with the neat double number, but then I do the same in Fahrenheit and I realize I don't end up with the double number in Fahrenheit, then that shows me that somehow that operation of doubling wasn't meaningful on that scale. And that's very important, right? Because we don't want to make the mistake of thinking we can be twice as smart. So that's the sort of key insight that they have and that they insist on. All right, so where does this leave us with these three senses of realism that I started with? Again, real as what must be presupposed, real as what's invariant across representations, and real as what is corresponding to what is out there. Well, it's pretty clear that they're very happy with real as what's invariant, right? That's a key element. I also think, because of their drawing on the axiomatic tradition, that there's a way of reading them as real as what must be presupposed. And that's something that I've worked on quite a bit. I've thought about, well, if we assume that the representational theory of measurement gives us a good account of numerical representation, then that can guide us towards thinking about what sorts of attributes, what sorts of features attributes might have that are numerically represented. So I'm happy with those two. Very unclear that they have said anything at all about real as what corresponds to what's out there. And that's much harder to assess from just the formal work. It seems like for that you need something else. You need to actually look at the experimentation. You actually need to look at how you assign these numbers. So one thing that has happened is that people have looked at this notion of empirical relational structure and said, well, it really depends on what you mean by empirical relational structure. In order, if you want to find out, what's out there, so to speak, right? And if you thought that what empirical relational structures are actual data sets or physical objects together with an actual measurement procedure, as some of the early work of RTM suggests, then you very quickly run up against a problem that Ehrenthal and others have pointed out. You seem to have a lack of you seem to assume that the qualitative data set already has the kind of quantitative structure, because you're already correcting for errors. You're already assuming that somehow these axioms will hold, because any actual data set will have outliers, it will have error, it will have all kinds of problems that don't meet the axiomatic structure. And that's even if you allow for idealizations like there being lots and lots of data that you don't have, right? You only have a finite data set. Slightly more realism-friendly readings of this are, well, maybe what's really going on is they're talking about possible data sets that you might collect with an idealized measurement procedure. Okay, well, that sounds a bit more promising, because you might think, well, then you can sort of build in all of these corrections, or maybe an idealized data-free model, error-free data model, which somebody like Supi's worked on models of data a lot. You might think that's what they have in mind. Or if you're me and you're a metaphysician, you might think, no, they're just talking about a kind of quantity out there, some property out there that they're measuring that has a really interesting structure. It's a kind of structured space, or it's a structured space of qualitative properties. So as a metaphysician, I've taken the sort of, I'm looking at the presuppositions route, and I've said what they're really presupposing is something like this bottom thing, and not one of these more applied things. And I've taken that and decided to run with it, and I've decided, well, this is really interesting if you're a metaphysician, because it shows you that we can use something like the representational theory of measurement to understand what quantities might be, what makes them different from other attributes, and yet they're quite different from what sort of the early axiomatizers thought they would be. They're not necessarily additive. They might not even be just ratio scale representable. So they're rich structures, I say, but they're not quasi-numerical. And I think that's a sort of combination of what's real is invariant, but also we need to take seriously what we presuppose when we put numbers on things. So we should count both of these things as real. So that's where I've ended up if you wanted to know more about how metaphysical you can get from formal theories. That's the place to look. If you want to go back to instruments, I completely understand. All right, thank you.
Thank you very much indeed, Jo. Okay.
I don't want to draw this into a long discussion. I have a problem with the word real, because if I look of what you said, real is what is invariant, it seems to me that you mean what is true, what applies is what invariant. But that means that only universals are reals and particulars are not real. So no, as I say, there is a difficulty with this word real, which I think is really warranting an in-depth description from a philosophy, because a lot of the things that you said obviously, to me, appear to be true, but can be confused with applying to what exists. And that is very, very difficult. So I just put it there like that, to know what you think about it.
Good, and I thought about using this, on the one hand, very unhelpful, and the other hand, very provocative term real. But I thought I'd keep it there because I think it shows that it's sometimes I think that you can read this invariance criterion as harmless, right? That's fine, sure, yeah. We just think about what's invariant between our representations, and we'll take that seriously. But I think insisting that what you're really saying then is that's what's real means that you have to reconsider. Do you really think that everything that only happens to be representable from this perspective is unreal, right? And in one of the papers I wrote on this, actually, I contrasted this sort of what I call structuralist approach, which is sort of only take what's invariant and take that as objective, and everything else is just some sort of weird subjective thing that you impose either conventionally or perhaps because you have a limited perspective on things, with what I call the perspectivist approach, which takes very seriously the idea that sometimes some things only show up from certain perspectives, but we shouldn't ignore them. And I think those are two really interesting, currently very live debated issues in the philosophy of science that do affect how we think about what science tells us about the world. If we think, Well, for science, what works best is we look only at the stuff that's invariant across representations. I think, again, especially in physics, people do want to do, because they think that gives you a sort of less anthropocentric, less sort of limited point of view. We might be missing out on things. And maybe there are areas of science where that's a problem. Maybe if it's not universal constants we're interested in, then it matters if we lose them, if we don't take them into account just because there's only a limited number of perspectives. So I agree that that's an interesting question.
Good. Yes.
Thank you very much. I'm also going the opposite way from the word real. Can you go back to your three types of real? Yes. An even stronger realism might take the bottom box and cross out corresponds to and replace it with is. And instead of some idea of correspondence, use a strongly realistic relation of reference between language and what is out there, including the possibility that there might be a mathematical out there.
Okay, very good. So corresponds here, of course, in the first instance to, because we're talking about a representation of some sort, right? So we're trying to find the element in the representation that we think, well, those things are reliable. Now you might think, well, here's a way in which a representation is, capturing something real. It's about that thing, right? It's a representation of that thing, and that thing I'm pointing to, I think that's what you mean by reference.
About is the key word.
Yeah, that's what we're realist about. Now, there are a couple of people, I think, would take that view and say, yeah, and if part of our representation contains numbers, that some of the things that these representations are about are numbers, right? Not attributes that are quantitative, but numbers, which is a view that you could have. It's a view that has some issues. You might think, well, that's very strange, because then some of the things that we're talking about in physics are abstract objects like numbers, and some of the other things we talk about are these things we measure with instruments that seem to causally interact with something, but they're not interacting causally with the numbers, presumably, because the numbers are abstract. So I think that's why that's an option that a lot of people would try to resist in the case of numerical representations, because they would like to avoid this commitment to numbers. That said, you do confront this question if, as Richard said earlier, if there is a value for the speed of light, if this is the speed of light that's out there, that's not up to us because that's a constant, is that a number? Or is that something else? Is that some physical attribute that we represent purely numerically, and that's what we do? Right? I think that's the issue.
Good, thank you. Next question is from the gentleman in the grey top there.
Thank you. I've been thinking in relation to this that the process of measurement involves an abductive jumping to the belief that the thing that you are observing is a certain thing. Then you apply your instrumentation as appropriate to it being that kind of thing. And the learning that you could come to would be a classification in the model that you have of that kind of thing. And so that is how I've come to understand what measurement is. And that's driven by the sense that the purpose of measurement is to go from a manifestation in the world to a decision about what to do in relation to that manifestation. Thanks.
Okay. So one thing I want to say quickly, which I think is right, is one of the types of inferences that you might think you're making in measurement or in much of science is an abduction. So one of the things that makes the correspondence problem the coordination problem seem so difficult is that you might worry that type of inference is always risky. It's always a very risky inference. And so obviously it could go wrong, and one sort of strongly empiricist instinct is to sort of back away as much as possible from that and sort of try to use that only as the last resort and treat whatever comes out of that inference procedure with caution, humility, and so forth. So I think that's one thing. The other issue that maybe you're alluding to, I'm maybe misunderstanding, is for many measurements we might think ultimately what we want is a decision, and you might think a decision often proceeds in a sort of more binary way. What am I doing about this? Am I going ahead with this project? Am I not going ahead with this project? Am I going to implement this policy, or am I not going to implement this policy? And so one thing that I think you do when you do that is you translate back from what is often a very precise and also a measurement that's surrounded by error bars to, all right, at the end of the day, we have to make a decision. And that decision is binary. That decision no longer captures, I think, the sort of fine-grainedness of measurement. That, I think, is an interesting problem. I think it's one of the problems we do see a lot in policymaking, where the translation from, well, we know a lot about this, we have a lot of data on this, but now we need to decide how to translate that into a decision is fraught and is value-laden. It's certainly not something that's straightforward at all.
Thank you. So, yes, next person there.
Thank you. That's fascinating. Quantum mechanics introduced the notion, certainly to the general public, that the observer affects the observed. Does this metaphysics you've been discussing have a view on this?
Not directly. It's a short answer to that. And so, I mean, there's a whole literature and philosophy on how we should understand quantum mechanics and whether we should understand it realistically or not. I think, in fact, Oxford is one of the places where most people are realists in the philosophy department about, that might have been news to some of you, but that's the case. So I think there's a majority philosophy view now that says, no, we should take as realist a view of quantum mechanics as we can and try to avoid the kind of Copenhagen view according to which somehow the observer changes what's going on in the measurement. One of the things this has led to is an interpretation that takes the mathematics very seriously. And so this does relate to this, this idea that we take the formal structure of things very seriously and let that guide our metaphysics. And that's certainly been done for the case of quantum mechanics as well, although I should stress I'm not at all an expert on that. So I'm afraid this is as far as I can answer the question.
Thanks.
Good. Next question is from Hasok Chang.
Thank you, Joe. I think we would agree that measurement is a success term, right? So if you say, I have measured X, that implies X is real, right? In that spirit, what do you think about the relation between data and the object of measurement? In other words, in your view, can there be data that don't actually measure anything real?
Well, so individual data, sure, right? So any individual data point might not be measuring anything real at all, right? I think the question is, if you've successfully generated data that can be modeled in a certain way that seems to match on to one of these nice, well-understood numerical structures, then that gives you pretty good evidence for thinking that there's something, some phenomenon that you're tracking that can be numerically represented in a meaningful and responsible way.
So successful mapping to a discernible formal structure would be the criterion?
Well, so the crucial thing is because you can distinguish the strength of these measurement structures, you can say fairly precisely what sorts of inferences you'll then be able to draw about the thing that you've measured. And I think that's what's of interest primarily, right? I mean, it's me, the metaphysician, who then wonders sort of what's really out there in the world. I take it most people who use measurements and try to represent what they've measured numerically are not terribly worried about that, but yeah.
Thanks.
Okay, good.
Thank you for the thought-provoking talk. The previous speakers implicitly all seem to be saying that if you have a kind of true categorical or ordinal variable which is not interval ratio, because you don't get a numerical output per se, that's not a real measure. Whereas you seem to be saying having a more inclusive view of what measurement is. And so I'm an epidemiologist, and a kind of debate I've been having with some of my colleagues is I kind of believe that if you are trying to answer a binary question, you actually only really need binary data. So you don't always need to get a true numerical measure, whereas most people seem to be kind of in love with Kelvin and think only kind of true scales count as numerical measures. So I was kind of wondering if you had any thoughts on why the kind of Kelvin dictum seems to have become so dominant.
So there are two questions. One is, what's my take on these different levels of measurement? The second question is, why is the Kelvin dictum so important or influential? So my own complicated view is that actually both interval and ratio measures are measures of quantities. But I'm also happy, and this also perhaps is in response to Hassel's question, I'm also very happy to say that there can be good and useful numerical representation of weaker scales. I think that's totally fine. I wouldn't call those measures of quantities, but that's sort of because I have these metaphysical commitments. Why is Kelvin's dictum so influential? Why is the sense that you only get really good knowledge if you have a numerical expression? I think on the one hand because you can draw these strong inferences, and that's very appealing. I think the other is that it can frustrate people if you put numbers on something and then you say, oh, but be careful not to misinterpret them, right? I think that then goes against this portability and transparency of numbers. And I think that's one of the things that's really frustrating. Whereas if you can say, yeah, here are the numbers and you can do whatever you want with it, you can throw any statistics on it, it will hold up, then that's appealing and that's nice. And people like that.
Thank you. I'm going to take the last question myself, actually. So you started off with 3 views, and the one that dropped out was the empiricist view, because what you ended up with is a sophisticated combination of an axiomatic view and an operationalist view. So what did empiricism get wrong, as it were? And what kind of empiricism are we abjuring if we buy into your account of measurement?
Certainly any empiricism that says sensation is the basics of experience, and our experience is basically sensations. I think that's just too weak. We just don't get enough science from that if we do that. I should say, I think it drops out of measurement theory. I don't think it drops out of measurement completely, because I think if you look at metrology and the metrology literature, then people do worry about some of these empiricist concerns and do worry about how you get from, including the semantic concerns, how do you get from a particular physical thing or a particular experiential thing, a particular thing you observed, to a particular numerical representation. So I think that question doesn't disappear. I think it just is better dealt with by metrology and the philosophy surrounding that than by measurement theory. Okay, the short answer.
Good. Thank you very much indeed. Let's thank Jo.